Okay, picture this. A sculptor, maybe under a skylight, hands totally white with clay dust. But he's not sketching stone, he's drawing. Waves. Waves that somehow fold up into perfect cubes and then they just unfurl again into these elegant spirals. And the really amazing thing, he isn't just drawing an object, he's drawing like a deal, a cosmic agreement, give and receive, compress and release, charge and discharge. And he has this deep conviction, that the stone will hold the motion, but only if the motion itself is true. That image, that's really our way into the mind of Walter Russell. He lived from 1871 to 1963, quite a span. And he was a polymath in the truest sense. A renowned sculptor, sure, but also an architect, an accomplished figure skater, believe it or not. But beyond all that, he was this self-taught scientist, a philosopher, kind of a mystic figure. He didn't just look at reality, he really tried to conduct it. So today we're doing a deep dive into his grand vision. It's like a cosmos that moves like music, defined by waves, octaves, spirals, and this fundamental law he called rhythmic balanced interchange. It's a vision that, well, it wasn't fully picked up by mainstream science, not in its entirety anyway, but it has some surprisingly resonant ideas we really want to dig into.
That's a really important point to make right up front. Mainstream physics never, adopted his whole system. And let's be honest, some of his specific claims, they kind of missed the mark. But underneath all the sometimes very poetic, sometimes mystical language, there's this really hard hunch. And it still clicks. It resonates powerfully with modern motion theory, the idea that the world is fundamentally structured motion. And that motion is always seeking balance through synchronization. It's a powerful idea, and now we have tools to look at it.
Right. So that's our mission today, basically. We want to translate the useful core of Russell's unique ideas, figure out what we can understand, maybe even test, discard the parts that don't quite hold up scientifically, and really find the bits that still sing with insight. We're hunting for that underlying pattern language he sensed, the grammar of balance, reciprocity, rhythm that he felt was just humming beneath everything. So just to give you a quick roadmap, Russell's universe has a few key ideas. There's this still magnetic light at the center, with electric motion spiraling around it in two ways. Then rhythmic balanced interchange, RBI, that's nature's give and receive pairs. He saw octaves everywhere. In chemistry, music, you name it, and the shapes we see. Cube sphere, vortex, and spiral, he thought they came from stress geometry. And finally, sext pairs, his term for complementary forces. It's a lot, but that core idea of rhythmic balance ties it all together.
Exactly. And let's maybe start with that still magnetic light. His descriptions were often, deeply poetic, almost spiritual. But if we try to translate that using the lens of motion theory, it becomes something really quite interesting. We see it more like the background synchronization field. Think of it less as, a physical light and more like the perfectly quiet stage, the backdrop for all the universe's activity. It doesn't move itself, but its presence is what lets all the other motions, all the actors on the stage, couple up and interact, dance together. It's the prerequisite for any kind of synchronized order.
Okay, so if the light is the still foundation, then the electric motion must be the dynamic stuff, the actual dance happening on the stage.
That's precisely it. That's a great way to put it. We see electric motion not as just random jiggling, but as these highly structured loops of charge, plasma, fields, propagating by what we call phase locking. Imagine like a symphony orchestra. All the instruments playing their own distinct parts, but perfectly in time, right? Synchronized, creating one coherent sound. That's phase locking. These are the waves, the currents, the resonances we actually observe. Organized, synchronized flows, constantly interacting around that foundational field.
Okay, right. So we have this still foundation, this dynamic motion. The next question is, how does it all organize itself? How does the energy move? And I guess that's where his rhythmic balanced interchange, RBI, comes in. It sounds almost philosophical, give and take, but what's the scientific take on these giving-receiving pairs?
Yeah, what's really fascinating here is that RBI, when you look at it scientifically, it translates pretty directly into fundamental conservation principles and feedback principles. It basically describes how energy and matter flows work to equalize gradients, usually through oscillation, and how systems naturally seek coherence, but always obeying conservation laws. You can't just create or destroy energy. Think about it. Stable order doesn't just pop into existence. It often comes from these closed loops exchanging energy or information without any net drift, just constantly adjusting until maybe something external pushes them to a new state. It's like the universe's way of, keeping its books balanced.
That makes a lot of sense, the balancing act. To make it more concrete, though, can you give us some real-world examples? Where do we see RBI playing out?
Oh, absolutely.
Yeah.
It's everywhere once you start looking. Take something really simple like an electrical circuit. You've got capacitors and inductors constantly swapping energy back and forth. Charge becomes magnetic field, magnetic field becomes charge, oscillating towards balance. That's an LC circuit. Biologically, it's the engine of life itself. Think ADP and ADP, NADH and NAD plus oxygen and CO2. These are all paired fluxes, constantly exchanging to keep metabolism stable, maintaining life while also dissipating the necessary heat.
Wow, okay.
Or zoom out to the whole planet, our climate system relies on it. Evaporation and condensation. High and low pressure cells swapping mass and momentum. Think about the Hadley cells, those huge atmospheric loops moving heat from the equator towards the poles. These are massive planetary scale RBI systems, always moving, always trying to find balance.
So it's almost like the universe has this built-in, incredibly sophisticated control system running everywhere, from tiny circuits to the whole planet.
Exactly. Yeah, from a control theory viewpoint, RBI is basically saying, drive the system until the error hits zero, but always allow for a bit of bounded overshoot. Systems don't just slam into a static balance point and stop. They tend to oscillate around these optimal set points. And coherence, that beautiful order arises when the phase lags of these oscillations are just right. Too little feedback. Things drift into chaos. Too much. You get wild instability. It's that constant, delicate, rhythmic interchange that stops everything from either flying apart or just grinding to a halt.
Okay, this next one from Russell always got me: octaves. He actually tried to map the periodic table of elements onto musical octaves, which sounds, well, incredibly ambitious, maybe even a bit audacious. What was he getting at there? What part of that intuition was maybe right, even if the details were off?
He definitely overreached trying to force-fit chemistry into strict musical octaves. That wasn't quite right. We know chemistry follows quantum numbers, the Pauli exclusion principle.
Yeah.
It's a different kind of structure. So his octave table was more, let's say, a poetic metaphor than a literal predictive scientific model.
Yeah.
However, his core intuition that periodic harmonic patterns exist everywhere, that was incredibly prescient, really insightful.
Okay.
Think about it. Atomic shells have structure. Rydberg series and atomic spectra show patterns. Molecular vibrations have specific frequencies, crystal bands, even stars. Stars ring like bells with specific frequencies, P modes and G modes. These are all real examples of preferred harmonics, natural notes, existing across totally different scales. It's like plucking a guitar string. It naturally vibrates at specific notes, and those notes repeat at higher pitches, the octaves. The universe seems to have its own preferred scales of operation.
So the metaphor was powerful, the core idea of repeating harmonic patterns, even if the specific mapping to chemistry didn't work out.
Yeah.
He saw the pattern maybe before we had the quantum mechanics to explain the why.
Precisely. Motion theory looks at these octaves as hierarchies of eigenmodes. Eigenmodes are just the preferred stable patterns of vibration or organization that a system naturally falls into at different scales. Structure, in this view, is basically captured eigenmodes. And complexity comes from nesting these repeating harmonics. It's a deep organizational idea.
And what about the actual shapes he talked about, the cube, sphere, vortex, and spiral? These seem to describe the geometry we see everywhere, micro to macro.
They absolutely do. Russell's idea that form arises from stress geometry, like compression favoring a cube or stillness favoring a sphere, it gestures towards a really fundamental physics principle: symmetry breaking under constraint. Think about Wolf constructions. They predict the equilibrium shapes of crystals based on minimizing surface energy, or soap films forming minimal surfaces, or even magnetic domains lining up in patterns. Motion theory kind of suggests that the geometry we see is like the shadow of which motions are allowed to synchronize given the boundaries and forces involved. The shapes aren't just random, they're often the most efficient ways to manage the flow of energy and information.
And the spirals and vortices, I mean, you see those everywhere, right? From cream in coffee up to galaxies.
And what's fascinating there is that logarithmic spirals, the specific type you see in cyclones, galaxy arms, even leaves on a stem, they actually optimize transport when things are rotating or growing. Spirals are basically how flows manage to conserve angular momentum while changing scale. They let things connect across distances with minimal friction or shear. So Russell, focusing on these shapes, he was really onto something. He saw them as nature's signature for efficient, balanced flow.
Okay, lastly, he talked about sexed pairs. Now, to modern ears, that language sounds, well, a bit dated, maybe. A bit archaic for science. What was he really getting at?
The language definitely sounds archaic today, you're right. But his underlying intuition, it was spot on about complementarity being fundamental in nature. He used sexed pairs to describe these basic polarities: compression versus expansion, charge versus discharge, positive versus negative, give versus receive again. In motion theory, we translate this into complementary operators, things like source and sink, clockwise and counterclockwise rotation, emitter and detector. These aren't really opposing forces fighting each other, they're dualities, two sides of the same coin, existing within a single dynamic loop. They always balance each other out, and together they give rise to everything we observe. It's that core idea. Every action has its necessary balancing reaction within the system.
Okay, so if we step back and try to summarize, what were the really big things he intuited, the things he got directionally right, even if his specific models weren't adopted?
I'd say there are four big ones. First, the universe runs on reciprocity. His RBI, that give-receive, points straight at bidirectional coupling.
Yeah.
Action-reaction, energy flows, reversible physics at the micro level, those metabolic pairs like ATP-ADP. Stable order needs closed loops exchanging stuff without drifting away. Second, waves and octaves are everywhere. Okay, he overreached on chemistry, but the basic idea of periodic harmonics, atomic shells, stellar oscillations, absolutely fundamental.
Right.
Third, spirals and vortices are key organizing shapes. They're crucial for efficient transport, conserving angular momentum, maintaining coherence and flows at all scales. He nailed that observation. And fourth, form follows stress. His cube sphere idea captures that deep principle that geometry isn't arbitrary. It emerges from symmetry breaking under constraints and forces. That's a pretty impressive list of insights, especially for someone working largely outside the scientific establishment of his time.
It really is. But it's also important to be clear where modern science, including motion theory, diverges. Where do we disagree with Russell's specific claims?
Yeah, we do have some clear points of divergence. For instance, that attempt to map the periodic table using musical octaves. Beautiful metaphor, yes, but not a predictive scientific scheme for chemistry. Chemistry really follows quantum numbers, the Pauli principle.
Right.
We can keep the insight about periodicity, but not the literal musical mapping.
Okay.
Second, his ideas about transmutation on the cheap, changing elements through simple chemical means. That's just not how it works. Nuclear transmutation is real, absolutely, but it requires specific high-energy nuclear processes, not tabletop chemistry or wishful thinking. And finally, reaffirm light as some kind of absolute physical stillness. While it's a helpful image, physically, that still center is better described by things like invariant measures, background symmetries, like Lorentz invariance, for example.
Lorentz invariance. Okay, that sounds pretty deep. Can you give us a quick sort of real-world sense of what that means? How does that relate to this stillness?
Sure. Lorentz invariance basically means the fundamental laws of physics look the same for all observers, no matter how fast they're moving relative to each other, as long as they're not accelerating. It's a kind of stillness or constancy in the rules themselves, a foundational symmetry of space-time, rather than a specific physical thing that's standing still. So for us, the modern view anchors on these abstract, unchanging rules and vacuum expectation structures, rather than a mystical, static light at the center. Being honest about these differences helps us salvage the really useful parts of his vision.
That makes perfect sense. So with that clarity, how does motion theory take something like Russell's poetic RBI and reconstruct it? Not just as a concept, but as something testable, like a control law we could actually explore in experiments.
That's a great question, because that's where his ideas become really actionable, not just philosophical. We can essentially model any system as flows, trying to flatten out gradients, differences in energy, concentration, whatever, while still maintaining the system's identity. Take mapping octave harmonic behavior across scales. We can actually try to predict material properties based on how coherent the vibrations are across different size scales within the material. We can map out these eigenmode stacks, those preferred vibration patterns going from the atomic level to molecular to the crystal lattice, right up to the macroscopic object. For instance, we could hypothesize and then test how resonant interactions between phonons, which are like quantized sound waves in a crystal, and electrons, might create specific conditions, maybe windows for superconductivity. This lets us quantify RBI, that balanced exchange, as something like loss-minimizing energy transfer, which is directly relevant to designing new materials.
Fascinating. So we're looking for these patterns of balanced energy transfer, trying to find the universe's natural rhythms to maybe optimize systems. What other kinds of experiments does this open up?
Well, another really exciting area is studying vortex conduction in plasmas, in magnetized plasma, right? We could deliberately seed counter-rotating vortices, pairs of spirals spinning opposite ways, and then measure how efficiently they transport energy or particles compared to just a single vortex. The hypothesis, directly inspired by Russell's idea of balanced pairs, is that these paired spirals should significantly outperform single ones. Less turbulence, more directed energy flow, because the interchange is balanced.
Okay.
We could also design tiny optical cavities, microcavities with specific geometric self-similarity built in. Then we test for photonic octaves, basically, seeing if we get harmonic ladders in leasing thresholds or directional light output. That would be realizing his octave-style mode, capture in photonics, but without trying to force chemistry into musical scales.
And it sounds like this could even apply to biology, understanding how life regulates itself.
Absolutely. In, say, metabolism engineering, we can now do real-time tracking of redox states, those electron transfers like NADH and AD+, and organoids like tiny lab-grown tissues. Then we could apply oscillatory delivery of oxygen or glucose, mimicking rhythmic supply and demand. We can test if these synchronized cycles actually improve growth and repair in these biological systems compared to just giving them a steady, constant supply. This brings RBI right into understanding biological regulation as a dynamic rhythmic balancing act.
And Russell's light concept that gets a scientific update too, beyond just Lorentz invariance.
Yes. For Russell, light was this still mind center, and all motion radiated out from it and returned. For us, the still part is more about invariance, the symmetries, the conservation laws, the causal structure that everything has to obey. That's the constant background. The radiation part becomes phase-matched propagation. Think electromagnetic waves, phonons, other collective modes moving through a medium that can carry synchronization information. And the return is dissipation and record. Motion eventually resolves into heat or gets locked into structure, or maybe even forms a memory trace. We can keep the poetry because it definitely holds valuable intuition, but we swap in precise instrumentation and testable concepts to actually understand the mechanics.
It's really quite remarkable how his background, being an artist and mystic, fed into these deep physical intuitions. He was connecting things that seem worlds apart.
Indeed. And it goes beyond just physics and chemistry. Think about attention in our own minds. Focus can be seen as phase alignment in brain activity. When you focus, you narrow the bandwidth and raise the coherence, something measurable in EEG scans as increased cross-frequency coupling. That's like RBI at a cognitive level.
Wow.
Or even just breathing. Slow, conscious breathing locks your heart rate variability to your baroflex system. It creates this body-wide RBI effect via the vagus nerve, impacting your whole physiological balance.
Huh.
Even music and architecture, Russell's original fields, spaces and sounds that maximize coherent standing waves can actually reduce biological noise. That might be why cathedrals or certain musical chords feel so profoundly ordered or resonant to us. It really seems like Russell was detecting a kind of universal operating system.
So as we start to wrap up this journey through Walter Russell's world, what's the fair verdict? What can we say about his unique, sprawling legacy?
I think the fair verdict is something like this. Walter Russell wasn't a textbook physicist, not by a long shot. He was a pattern hunter. And while he definitely overclaimed on some specific scientific mappings, his core insistence that nature is fundamentally reciprocal, rhythmic, and balanced, that wasn't naive. It was just maybe early. Motion theory, you could say, uses his compass, but not his detailed map. We translate his poetic RBI into the more rigorous language of control theory, non-equilibrium thermodynamics. His octave talk becomes eigenmode stacks. His spiral talk becomes conserved flow geometry. And his light talk gets translated into concepts like invariance and phase-matched propagation.
So for you listening, the takeaway seems pretty clear. If you go looking to Russell as some kind of prophet with all the final answers, you'll probably, well, crash. You'll find more poetry than provable science. But if you approach him like a poet who somehow smelled the underlying operating system of the universe, then you can definitely build on his insights. There's rich ground there for understanding the world.
Exactly. And maybe a final thought to reflect on after this dive. Consider this. Reciprocity is the grammar. Synchronization is the music. These seem to be the fundamental principles orchestrating just about everything we see, from the tiniest particle interactions up to galaxies and even inside ourselves.
What an incredible thought. It really does change how you look at things. And it leaves us with maybe one more thing to ponder. Balance isn't really stillness. It's oscillation that doesn't drift away. It was always about motion. Russell, he heard the backbeat. He felt that underlying rhythm in everything. And now, with the tools of modern science, we're finally starting to bring the meters, the instruments to measure that music. So maybe go out there and try to notice the rhythmic, balanced exchanges happening all around you in your own world. They really are everywhere if you just listen closely enough.